Hi, everyone. Thank you for coming and staying up for the last talk. So we're going to present something that we have been working on for about 2 years or more. It's a suite of algorithms for clustering and classification of time series data. And what makes it different from existing tools. There are quite a few points of difference. I'm going to go over them. But the key difference is that we take advantage of the underlying dynamics of the process that is generating the time series when we are coming up with metrics that feed into our classification algorithms. It'll make more sense what I mean by that as we go along. So this is my lab. Uh, we are a computer science lab at the University of Chicago. Is my postdoc. She actually just very recently left for a national lab position, and pretty much everyone else is a computer science student. So we are what we do in our group is look at hard problems of data science, particularly related to biology, biomedicine, or social sciences. And we are interested in not just using machine learning as an off-the-shelf tool, but looking into problems which require design or improvement of existing algorithms. So this is, I guess everyone in the audience is very clear about what classification is. And there's a kind of a non-exhaustive list of the different algorithms that exist. Many times when you're talking about classification, or many of the algorithms that do exist kind of apply out of the box to tabular data or structured data. And but not all of them. I mean, if you have time series, you can look into recurrent networks or variations of those, LSTMs and stuff. The problem with that is you need a lot of data to actually train a neural network. And while some time series are long and have lots of data, but that might not be true for every problem we come across. Sometimes the amount of data that we actually have access to is not enough to train a neural network well. So in those cases, we actually have to fall back on something like a tabular some algorithms that work on tabular data, like, I don't know, random forests, gradient boosting, XGBoost, and all that. The issue is when you're talking about time series, it's not clear what the feature vectors are. I mean, you could kind of assume that the time series entries are the feature values themselves, but that kind of creates issues. That's not really a natural way of looking at time series. That's one. Also, the time series lengths might be different. So somehow you have to do some kind of artificially guarantee that they will have the same number, same time series lengths and all that. So it's not quite natural to treat a time series as a feature vector. Also, you would want to kind of take advantage of the fact that it is a time series. So there is a causal direction in which information flows, and you'd want to take advantage of that. So how do we actually come up with general classification algorithms? Of course, you could also use models like Garch models or ARMA models to model time series and kind of figure out that, okay, this time series example has a different model than the other one, and hence they're different, and do classification in that manner. But that kind of doesn't work very well when you have, say, categorical data, or when, again, if you don't have too many entries in your time series, that will cause a problem. So that's what I actually just said. Probably should have used this slide, that when you look at neural networks, you can use raw streams more or less, but you require a lot of data. If you want to use algorithms that are typically applied to tabular data, you need to map them to features. So what is the right feature to use? That's really the core problem that we looked at. And can we tie such featureization to generative models of the underlying processes, the physical processes? So let's look at that. So it started with trying to come up with generative models from data. So think of a data stream. In this case, I've shown this is an example of a binary data stream. So you can kind of mentally replace that with any quantized version of any finite quantization. It doesn't have to be binary, but it's kind of in this case a binary data stream, and we want to come up with the optimal stochastic generator of that process, right? You have to assume certain things. If it is completely unbounded, then you'll never be able to come up with any kind of model or reason why that is a good model as opposed to another one. So we assume that, let's say, the underlying processes are at least in some sense stationary. They're not changing too fast. And if you assume that, it turns out, and I'm not going to go into all the details of this, that you can come up with something which looks like a graph with probabilities on the edges, and essentially a finite number of states with transition probabilities between them. So they have Markov property built into that, but it's kind of slightly different than a standard Markov model, standard hidden Markov model. And why is it different? It's different mainly in the sense of the algorithms that are used to actually do this map that I am showing on screen, going from this data to this model. So note, and I want to stress this outset, that you're not being told that there are two nodes in the graph or two states, that the wiring is like this. You don't know any of that. You only have the data, and from that you want to go and find this model and somehow convince yourself that that is the best model in this case. And if you change the process, then these probabilities will change, as might the number of states, as might the connectivity. So this is an algorithm that was reported a few years back by our group, or 2013, I think. Since then, we have modified that and improved that, proved bounds on sample complexities and all that. We're not going to all of that. It's called Genesis. And typically what we are talking about here is something like this. You can look at different processes of different complexity, and it will not typically be obvious by looking at frames. Yes.
So sorry, I was trying to ask a question that I couldn't mute myself. Can you just go back to the previous slide, or oh, maybe this one? Can you just briefly explain how? So I guess this is a Markov chain, or what exactly is? I mean, how do you use this graph on the bottom to generate the binary sequence?
So it's you can imagine this is like an ergodic stationary process. So it doesn't matter where you start. You choose any one state and you generate the symbols according to the symbol generation probability. So sigma 0 generates a 0 with a probability of 0.7. It generates a 1 with probability of 0.3. And then if you actually generate a 1, then you switch the state. Then your symbol generation probabilities change. And then if you generate a 0, you come back here and you keep going that way.
I see. Okay. All right. Yeah. Thank you.
But the non-triviality is that going from that model to the data generation is trivial. The non-triviality is going from the data to that model, because, as I said, you don't know how many states there are, how they're wired. So if someone told you that there are only two states and here is the wiring, you would just very trivially find the probabilities. But you can't do that because you don't know what the structure is. So, for example, if you the data streams visually, or even some naive statistical tests might look very similar, but their underlying generative model might be very different. So the first one here, this is just IID process, just random walk. And these are, well, in some sense also random walks, but there's more structure to them. It's kind of not a non-IID processes. Right. In this case, there are two states, and in this case, there are 6 states. So also probably it's important to note what it means to have 2 states in this case. It means that anywhere in that data stream, you have really 2 contexts. And in this case, since there are only 2 states and it only matters, the state only depends, if you look at the structure, on the last symbol. So it depends on what the last symbol was. That kind of determines your current state and determines what the next symbol distribution would be, right? There's only 2 of them. That's what, when I say that this is the correct model, then the idea is that there are only 2 such states in the process. I don't know that, we refine that. And if there can be more, they can be more complicated and so on. Things can be way more complicated.
Sorry, so just another quick question. So, so here the probability to jump between states is the same as the probability of generating the different symbols, but I mean, intuitively, it would make sense to have these sort of decoupled, right? So at each node, you have a certain probability of generating, say, 0, 1,
Couple
and
them,
then
you'll not be able to run the kind of algorithms that we want to learn. It will become something like a standard HMM, where it would be very difficult to learn these things. It would be very difficult to understand the structure. I mean, you can't have it both ways. You can actually set out saying that there are n states and they're wired in this particular way, and then you can have a symbol ejection probability and a state jump probabilities all different. Great. But if you want to do that together, then that will quickly become intractable.
okay, so so you're making this assumption because it simplifies your computational cost, so your problem.
It's not really an assumption. It's like we are saying that we are going to model processes which can be represented in this framework.
Right. Okay. Sure. Okay.
Right. Yeah. And we're not going to be able to go into that, but actually you can show that the class of processes that can be modeled by within this framework is actually pretty large. In fact, it kind of goes up to more kind of general dynamical system models that have been proposed before, like PSRs or observer OMs. I forgot what the middle O is. So yeah, it kind of goes up to that very general, but by doing this particular framework, you have a very efficient algorithm for actually learning these things. You can prove bounds on sample complexities. You can show that you can efficiently learn them, and you can actually get something similar to pack learnability. So getting good models with high probability. Right.
Okay. All right. Thank you.
And the learning algorithm, I'm just going to outline, not going to go into proofs or anything of that sort, but it's very simple. So what you do is something like this. You start with the data stream and you really count symbols. For example, if I say, if you see 1, 1, 0, 0, what is the probability of getting a 1 after that versus a 0 after that, right? So for that, what you do is you just count 1, 1, 0, 0 in overlapping sense and see how many times it gets a 0, how many times it gets a 1 after that. That's incredibly simple. It turns out that if you have long enough data, then that actually will start converging pretty fast, like exponentially fast, to the true underlying probabilities, if a model like that exists. And we call these symbolic derivatives. And you can actually start building this kind of a lexicographically ordered table, which is you start with an empty word and ask what is the probability of seeing a 0 versus 1, which is just a symbol frequency. And then you ask, if I see a 0 anywhere, what is the probability of seeing a 0 after that versus a 1 after that? And you start tabulating that, and you would see what will happen. Not generally, there are more complications that show up, but I will not get into that. For a certain class of processes, what you will see happen is these probabilities will essentially cluster into groups. If they're actually two states, then you would see that living out a finite number of rows at the top, they essentially neatly kind of fall into roughly two groups. In this case, you see there are 0.7, close to 0.7 and 0.3 and 0.9 and 0.1. And using that, you can start building up the model as follows. You start with the one state, label it with the empty word, and then you look at the next symbol, lexicographically ordered 0, which is not the same thing. This vector is not the same one as the one for the empty word. So you create a state. And then you look at the next symbol 1, you see that doesn't match with either of the first two. You create a one more state. And then you look at 0, 0, you see that actually kind of is very close to the first one. So that kind of gets actually a self loop. And then you keep doing that, and you would see that you'd essentially close up. The algorithm will terminate itself. And then if you take the largest strong component of it, then the connected component, strongly connected component of it, then you get a model like this. And again, what is built into this is the assumption that we're looking at an ergodic stationary process. Without that, you'll not be able to make this jump right there. But once you have the structure, you can actually find the probabilities very, very easily. You can just start at any one state, just to go around the state, see how many times each link is visited, and normalize that. That will give you that model, right? And one point, of course, is that things will not match up exactly. So there is a error resolution under which you're merging things. And it's important to note that if you make that too big, the resolution at which you merge things, then the whole model will collapse to a single state. And if you make it too small, then it'll essentially become a tree where nothing gets collapsed. So it's kind of two extremes are there. And now going back to our question of mapping time series to feature vectors, right? So we're going to go into more details on this, but one of the tools that we use, one of the algorithms that are there in this Timesmash suite of algorithms or tools rather in the Python package is to use these symbolic derivatives as a feature vector. And you can use as many of them as you want. More the better, of course, but well, there's only a finite number you can use. So that kind of gives you like a way of mapping a time series to a set of feature vectors. That's like one way of doing that. But we're going to do more fancy things, which I'm going to talk about in a moment. Yeah, that's what I was just saying. You can take one of these and use that as a feature vector. You could use that. That kind of works in some cases. But we are going to do something more kind of a little more interesting. So before we do that, the reason why we are saying that this actually is process aware is because when you're modeling things like that, you are essentially trying to come up with a model of underlying generating process. It might not be correct. It might not be, the actual process might be way more complicated, but the number, as I just said on Eric's question, that the class of processes which can be modeled in this framework is pretty large, actually. So, you have a good chance of getting something close. And you can make those statements mathematically precise. So, so once we have that, something like this, how do we use this for classification or clustering? We do something like this, right? So we have, say, a classification problem. There's a class 0 and class 1, and it's all time series problems. So your class exemplars are all time series fragments, and you use this particular algorithm to find models in each of these classes, and then if they're different models, well, then they're different. That's one way of looking at it. We're going to do actually something even more interesting, but that's one way of looking at it as well. Now, the most interesting part of this, like where all of this comes together, is the idea that we can actually bypass, in some sense, the modeling, right? So we can ask that given a single time series fragment, and if someone tells you that they're generated by either model A or model B, which one is more likely? What is the log likelihood of this data being generated by A versus B, right? A very standard formulation. We have to do a little bit of work because we are not entirely in a standard setting, and that work involves defining how to calculate log likelihoods efficiently for this particular framework. And we start with kind of the definition of entropy rate of Markov models, really, for probabilistic finite state machines, as we call them. That's pretty standard. That's not something that we did. That's we can just read off from any standard text. Then we kind of define a slightly generalized version of KL divergence. So KL divergence is most of the time used to define compare and contrast probability distributions, right? But here we want to use a kind of similar idea to compare stochastic processes, which might not be IID. So you have to generalize that a little bit because it's not really just one distribution. It's a stochastic process, which you cannot assume that all the distributions of all the variables are the same because they might not be IID. So we generalize that. It's almost a straightforward generalization. And then we can see that essentially this is the most important equation in this context, that if you compute the log likelihood of a sequence or a time series fragment being generated by an incorrect model, then an additional term shows up. Again, this is what we expect from standard notions of coding and information theory. If the models match, then the KL divergence would be 0, so this term will disappear. And if your models do not match, then an extra term appears. So if you take a time series fragment and you have a bunch of models, then you can see which one gives you the lowest value when you compute the log likelihood in this manner, or rather the maximum value, depending on whether you include the negative sign or not. And that essentially would be like an NLE solution to that problem, which one is the best model. All of that, at an abstract level, this is all very obvious. The contribution here is to kind of carry this out in this particular framework. And this is the algorithm which kind of allows you to compute that from sequences. Now, here's something that becomes very interesting. So what I just said is, what I just talked about up till now, is that given a particular set of models, known set of models, you can compute what is the log likelihood of a data stream being generated by any one of those models, right? So if I give you a set of models, I give you 4 models and a data stream, then you can compute the log likelihoods of model of the data stream being generated by each of those 4 models. You get a length 4 vector, right? Now, if I give you a different data stream, you can compute again as different length 4 vector. And if you kind of compute the, say, the norm between or difference of those 2 log likelihood vectors, is that notion, does that give us a notion of a distance? That's the interesting question that we asked. And the answer in general is no, because there can be two very different processes which give you the very same log likelihood when you fix the model, right? It turns out that when you choose a finite number of random models, then what you get there, that the norm of the difference of log likelihood vectors with a high probability approaches an actual metric. So that's really the non-trivial result that allows us to kind of use the tools that I talked about right up till now and make that and use that to come up with a metric between ergodic stationary time series samples, right? And we compare it with existing such ways of defining distance between time series. And probably the most well-known algorithm for that, or the most well-performing algorithm for that, that's the state of the art, is a dynamic time warping. And we extensively compared that, and we can show that our performance is better, and we are really an order of magnitude faster than DTW. And the proof of the statement I just said that it's not there in the paper that is submitted in this conference, but you can look it up on the preprint that is included there. So now let's talk about a little bit about what we can do. Something more fancy with this, actually. What we can do is we can interrogate in a classification problem. When we are given a set of exemplars for a particular class, we don't have to always assume that all those exemplars are coming from the same underlying process. They probably are, because they are, well, exemplars of a particular class, but maybe they aren't. Maybe there's actually substructures or subclasses which were not important enough or when the classes were made, right? So then what we can do is we can do a clustering within each class and come up with different models within each class and treat that set of models as representing that particular class, right? And then use a log likelihood to solve the classification problem. So this is what I'm talking about. You find clusters within the training classes, you find models for each of those clusters. So then each now class is represented maybe by more than one model, at least one model, but more than one. And then you essentially compute your log likelihood vectors to find the distances between the classes and solve your classification problem that in that sense. So this kind of gives you a cartoon for what I'm trying to talk about. Say class 1, and this whole thing is class 0, but you can, since you have an unsupervised way of finding distances, intrinsic distances between time series fragments, you can find maybe a subclass that is actually distinct. And then you find a model for this blue dots and this yellow dots separately, 2 models for class 0 and 1 model for class 1, and that will probably make your classification better. Actually, it does. We can show that.
So just kind of a naive question here. So the class, the blue is overlapping with the orange here, but don't you want like non-overlapping?
Yeah.
Classes,
overlapping,
or like, what's the point of this?
Yeah. It signifies that the problem as specified has class 0 and class 1, right?
Right.
But you can actually inspect or interrogate the structure of the exemplars within each class and find clusters between them, right? So yes, it's probably can have a better visualization. I probably should have another circle here, like an orange circle, and the class 0 is like a
okay, yeah,
right? So the actual pipeline is slightly more complicated. I'm not going to go into details of that. Essentially, it gets more complicated because the data might be continuous, and all of these that I'm talking about actually requires quantized data. So you have to kind of do the quantization in a manner that doesn't lose too much information, and then you have to quantize the training data and make sure the same quantization is applied to a test data, and all of those kind of leads to some complexities. But the basic idea is what I described. And let's see some results, how this works. So this is DTW, and this is kind of a standard problem from the UCR, the 4A data set. And the DTW kind of struggles with it. You see that these are the red points and the blue points are the two classes, and it has not separated anything at all. It's just like a bunch of sphere. Whereas if you look at if you use the log likelihood distance that I just talked about and use it in conjunction, that just gives you a metric. That just gives you the features. You can now kind of use any one of your tabular classifiers that you want or like to solve the classification problem, and you can see that it kind of does separation way better. It's not perfect, of course, but it is actually way better than what the DW actually is able to do. Not only that, you can, and I don't want to go into a review of the dynamic time warping algorithm, but it turns out that it is kind of easy to break that. So for example, if you have time series where things like this happen, say a binary time series with the probability of 1, 0, and 0, 1 are identical in the two classes, right? If that's the case, then no matter how hard you try or how hard DTW tries, you will not be able to distinguish them. It's just kind of built in the very structure of the algorithm, whereas that would be a trivial problem to solve for in our approach. And it's just not one example. You can get an arbitrary number of examples in this matter where DTW would keep failing. So this is really like a way of breaking DTW in some sense. And this is like the complete list of pretty much, we took out some examples which were too short, but pretty much the complete example set of UCR problem database. And you see the red points our CH is our algorithm. We call that clustered HMM classifier. The name is still evolving, so that might change in future. And this is the baseline, which is really DTW. And you see that when it's red on the CH, then we do better. When it's red on the baseline, then DTW does better. Kind of a better kind of breakdown, 60%, 61% of the time we are doing better. 37% DTW is doing better, and there's some ties. So we kind of do better on average. And in fact, it's not about getting, it is not really like a vote. If you can get some problems where I do better, that itself is worth is interesting, because no one algorithm is going to be better than everything else. And there's one application where we look at classification of gates. I'm not going to go into that in too much details, but this is kind of the other second application, which is not, it's kind of stated very briefly in the paper in this conference. But is under reviews elsewhere, is kind of very interesting. So because we can use this this kind of intrinsic similarity between time series, we can actually translate knowledge from one problem domain to another. So one of the things we did was look at the patterns of communication of flu, not communication, but the epidemiological patterns of seasonal flu, and use those patterns to predict weekly COVID counts. And that works out actually really, really well. This is our score compared to the mean absolute error, compared to a host of other teams who are participating right now at the National Forecast Hub backed by CDC. And this does not necessarily mean that we are the best team in every possible manner. I mean, this is one metric you can look at. The other metrics you could look at, in which you can probably the second or third team might change position. It also is a kind of sensitive to up to what time you look at. The couple of weeks at the end of December where we lost the first position to second or third. So it kind of changes a little bit at the top, but it's kind of definitely one of the top teams that are predicting the weekly COVID counts. And the software is available for testing your own data or experimenting with it, do what you want with it. It is on PyPy, you can install it. This is the GitHub repository that's pretty much open source. The part that is not open source is the Genesis algorithm, which is compiled as a binary. That seems to be the most expeditious way of sharing the data, mainly because it runs, and one of the constraint is that you need to have a Linux machine to run this, because the underlying compiled binaries are compiled for Linux targets, which probably will change in future. As soon as they can convince someone else to actually write that in Python or produce Windows binaries for it. But the running it is kind of very simple. We have tried to follow the sklearn kind of approach to it. We import it, and then this is your train data and test data, and you kind of do a fit transform. It's kind of a very standard approach in sklearn kind of workflow. And once you have the features, then you can use whatever classifier you want to use. Here we are using a random forest as in this example. You could use anything else as well. There's another example where you can, as is showing that random forest or support vector machines or add a boost. Again, it's pretty much the same thing. Create the features, you can do whatever classifier you want downstream after that, right? And this one, let me see why I included that one. This one is this is the actual example from the UCR dataset. It's called the dataset name is trace. That's like a standard name. If you go into the UCR database, you can find that dataset. It's also there in the included in the PyPy package and on the GitHub repository. And also it has a binder enabled on it. So if you go to the page, there is this badge there, as they call it. And if you click on it, then it will bring up essentially a live window where you can test your data without installing anything. So on a Jupyter notebook, a live Jupyter notebook. So that's pretty much what I have. Let me see. Okay, one more slide. So the general tool for time series analysis. It is aware of the underlying physical processes. It doesn't model every physical process with arbitrary complexity. There is obviously a set of processes or a set of complexity that it can actually target. But it has low sample complexity. It is not meant to kind of replace language models or models where RNNs or LSTMs do really well because you have lots and lots of data. It's particularly useful where you are looking at a few classes and you don't have oodles of data to work with, but you still need to actually map time series to features and solve the problem. And you can test it out with your own data. If you want us to look at it and you have interesting data to look at, that we'll be very happy to look at that as well. So that's what I have.
Okay, thank you so much. So I'll take Eric will take over, and if you have any questions, please speak up or just put it in the chat. Okay. So go ahead, Eric.
Okay. Yeah, thank you, Harry. So Harry needs to go for his teaching, so I'll just help a little bit with just wrapping up your presentation. So yeah, well, thank you very much, Shelly. It was a great presentation. Very, very nice. So I just had a quick question to get started, and maybe other questions from the audience. So again, if you want to ask a question, you can raise your hand, or you can type it in the chat. Then I'll let you speak. So I kind of missed. So I'm not really familiar with this class of methods, so I sort of missed the how you create features from the time series. Can you go over that again?
So how you create features from the time series. So
right, I think you mentioned this at some point, but I kind of missed that.
So a couple of ways of doing that. So in the package, there are actually multiple tools with which you could do that. The first one, the simplest one rather, and might not work all the time, is to do something like this. You take the time series, essentially you look at we call it symbolic derivatives. Essentially, if you see a particular substring, what is the probability of seeing a 0 or a 1 after that, right? So you can get you can generate as many features as you want from that.
And so what are the two columns? They just sum up to 1, or is something else?
It sums up to 1 if it's a binary stream. So you can't get, if you have an array stream, you will get 1 minus of that because it doesn't make sense to add have all of that, right?
Okay.
So so you can do that. That's kind of very simple. Well, it still works actually well in some cases, but that's kind of one of the things to include because, well, it's kind of easy to include. But the really interesting ways of generating the feature is to do something like this, right? So you have the time series, and you can look at if you have a bunch of models and you know that those models, one of those models is generating the process, then you can compute the log likelihood of the process of the time of the data stream being generated by model 1, model 2, model 3, model 4, right? So those are your features in some sense. But you can actually leverage this particular fact to do the following. You can actually do something like this, that if you have multiple time series, then you can figure out what their and these are given to you. These are exemplars, right? The 2 exemplars in class 0 and 3 exemplars in class 1. So you use this compression, this modeling algorithm, or this model inference algorithm to come up with your model, which is in this case might look like this, in this case might look like that. And then when you have a particular test stream, you can ask what is the likelihood of that being generated by this model versus that model. So that gives you
right.
2 features. Now, you don't have to stop there. You can generate more features by kind of first doing a clustering on this in each class and generate a bunch of models here, not just one model, right? So then you have really a larger number of features. But the number of features you generate and the complexity of that or whatever, all of that really is not entirely up to your control, but it's kind of driven by what the complexity and what the dynamics, the underlying processes are, right? So if it's like a random walk with IIT random walk, and then no matter how hard you try, you'll get one model, right? So.
Right. Okay.
So that's
great.
Yep.
Right. Okay. Thank you. Yeah. That helps. Yeah. This is great. Thank you. So let's see, any questions from the audience? So if you want to raise your hand or again ask in the chat. I guess no other questions. Yeah, so I pasted in the chat some of the links to some of the things you mentioned. So yeah, your COVID-19 definitely looks really nice. So and yeah, it's very impressive how you're doing in this competition here. Yeah, so that's
yeah, and this the link to the presentation will be there. It could be posted I guess in the conference, and also the link will be there live, so you can take a look at that.
Oh, sure.
And if anyone wants to kind of connect with our group, then they are more than welcome to do so.
Okay, great. Well, let's wrap it up